The first step in any examination of data is to know your data. Where did it come from? Who collected it? What is the sample of, and who is omitted? What's being measured? Sometimes you'll find people who don't even know the units. A Likert scale asking people to rate feelings on a scale of 1 to 5 is different from a scale rating 1 to 10. Data visualization is really important. This arises from two basic facts. One, we're drowning in data, and two, humans have good eyes. We're drowning in data because increasing computing power makes so much more available to us. The data piles up, nobody's even looking at it. Online store might generate data on the thousands of clicks simultaneously occurring, but it's probably just spooling onto some server's drive. It's just like spy agencies that harvest vast amount of communications, voice, emails, videos, pictures, but then can't even analyze them. The hoped-for solution is to use our fundamental capacities to see patterns, convert machine data to visuals. Humans have good eyes. We evolved to live in the African plains, watching all around ourselves to find food and avoid danger. Modern people read a lot, but that takes just a small fraction of the eye's nerves. The rest are peripheral vision. We want to make full use of our input devices. But putting data in a visual form is really tough to do well. Textbook has many examples to help you make better charts. The homework will ask you to try your hand at it. You might have forgotten about histograms. A histogram shows the number, or fraction, of outcomes that fall in a particular bin. For example, here's a histogram of scores on the final exam for a class that I taught. Histogram shows a good deal of information, more than just a single number could tell. Although this histogram here with so many 1 or 2-step sizes could be made much better. Often a histogram is presented as there with blocks, but it could easily be connected lines like on top there. The information in the two is identical. Histograms are a good way of showing how the data vary around the middle. This information about the spread of outcomes around the center is very important in a lot of human decisions. We usually don't like risk. But note the choice of horizontal scaling or number of bins can be fraught. For instance, consider a histogram of student grades. If we leave in the A- and the B+ grades, etc., we show a histogram like that on the left. But collapsing together into A, B, C categories, we get something more intelligible up on the right. That shows the central tendency much better. The student has gotten a lot of B grades, slightly more A than C. The previous histogram had too many categories. It was difficult to see a pattern. Another reason to show the data is to reveal structure that simple averages wouldn't show. Consider the datasaurus, where each scatter plot has the exact same X and Y means, same standard deviations, same correlation. Those simple summary statistics would entirely miss any of those patterns. Rawr. To find the center of data, we can calculate any of the average, sometimes called the mean, sometimes called the expected value, or alternately the median and or the mode. After that, we move to calculate measures of the spread of the data around the middle, the variation. There are a few basic calculations that we start with. You need to be able to calculate an average. The average of some values, x, where there are n of them, is the sum of each of the values, indexing them by I, divided by n. The average of x is sometimes denoted x bar. But the average value of a sample is not necessarily representative of what actually happens. There are a lot of jokes about the average statistician who has 2.3 kids, or the statistician with a higher than average number of arms. If there are 100 employees at a company, one of whom gets a $100,000 bonus, the average bonus was $1,000. But 99 out of 100 employees didn't get anything. A common graphical interpretation of an average value is interpret the values as lengths along which weights are hung on a sort of seesaw. The average value is where a fulcrum would just balance the weights. So suppose a student is calculating her GPA. She has an A worth 4, A minus 3.67, a B plus 3.33, a C at 2, and one F, 0. having troubles. We could picture these as weights, like at the top picture. The weights balance at the average point. There, the purple is the balance. But the bonus example that I said of, one person getting $100,000 while the other person, 99 people, get nothing, that would be example there, 99 weights at 0 glommed on, one person with such a long moment arm, that shifts the center of gravity away. So the bottom line, the average is often a good way of understanding what happens to people within some group, but not always good. Sometimes we calculated a weighting average using some set of weights W, so we modify the formula a bit. Your GPA, for example, weights the grades by the credits in the course. Suppose you get a B grade, 3.0, in a 4-credit course, and an A grade, a 4.0, in a 3-credit course. You'd calculate GPA by multiplying the grade times the credit, sum divided by the total credits. That's 3 times 4 plus 4 times 3 divided by 7 total credits. That's a weighted average, 24 divided by 7, 3.43. The average is sometimes called the expected value. That's perhaps even a worse name than mean, because again, the expected value is not necessarily representative of what actually happens. This can be an issue interpreting research studies. 2 interventions could have the same expected value, but one gives a 10% improvement to every person. The other gives a 100% improvement to 1/10 of the people. That's the same expected value in the technical statistical sense of those words, but really different expected values in the ordinary human sense of those words. There are other measures of central tendency. The median is another of what happens to a typical person in the group, again like the mean, but with its limitations. The median is the value that occurs in the 50th percentile to the person or occurrence, whatever, exactly in the middle. If there are an odd number of outcomes, otherwise it's between the 2 middle ones. In the bonus example I talked about above, where one person out of 100 gets 100 grand, the median bonus is 0. Those 2 statistics combined, that the average is 1,000 but the median is 0, can provide a better understanding of what's happening. Of course, in that simple case, it's easy to just say that one person got a big bonus and everybody else got nothing, but there may be other cases where aren't quite so extreme, but still pretty skewed. The mode is the most common outcome. Often there may be more than one. If there were a slightly more complicated payroll case, where 49% of the employees got 0, 47 got 1,000, and 4 got, 13,250 each, the mean is still the same. The median is now equal to the mean. Check those calculations. But the mode is 0. So that gives us a little additional information beyond mean or median. Now, each of these middle values is the solution to a different functional problem. We'll come back to that.